Hello everyone, I welcome you all. Today we'll continue with your next numerical of stiffness matrix method. So this is the numerical that we will see today. Continuous beam ABC is provided to having the central point loads in both the spans AB and BC of 24 kN and 12 kN respectively at a 5 meter apart from each support. Now condition is provided to you in this numerical that your support B, it is sinking by 30 mm over. Okay, and EI value is provided to you, that is equal to 3800 kilonewton meter square. So you have to solve this by stiffness matrix method. So we'll proceed for the solution. The first step, that is what you have to calculate the degree of kinematic indeterminacy dk. So kinematic indeterminacy for A joint, that is fixed, so it will be 0. Next for B simple support, it will be 1, and for here C it will be again 1. So total decay you will get equal to 3. Those are theta B, I assume those in clockwise direction, and theta C. So I'll assume, suppose theta B as your first redundant and theta C as your second redundant point over there. So I'll mark those points over here. So this will be my first redundant point and this will be my second redundant point over there. So first is rotation and second is again rotation, that is both are dealing with theta value, right? Now in second step you are provided with the basic equation. So basic equation is what? That is F is equal to ADL plus S into D. So one by one you have to calculate all these matrices here. So first matrix, that is F matrix. So F matrix is what? You will be having here F1 and F2 values because two coordinates you are having. Okay, so F1 and F2 values, what you have to see, are there any corresponding forces or moments provided to you at your selected coordinates or not. Okay, you have to see whether any corresponding forces or moments are provided to you. Check whether you are having no at point B and at point C, both you do not have any external forces over there or external moments. So both of these values F1 and F2 will remain 0. Okay, so here F matrix is done. Next we'll move for ADL matrix. So ADL matrix you will be having two values again, ADL1 and ADL2 over there. Okay, so for this what you have to do, you have to restrain the complete structure because you have to calculate the friction moments. ADL is what? These are the friction moments or the restraint actions, corresponding moments coming due to the live load or given load over, right? So for that what we'll do, we'll restrain your structure over here. So here I'll write restraining the structure. Okay, so here joint member AB and member BC. I'll restrain all the points here and whatever loading is given to me, that I'll keep as it is. Okay, this is my A, B, again B and C. So whatever friction moments you will be getting, that will be at this point and this point. Okay, this will be your clockwise in nature, this will be anti-clockwise in nature. Restoring moment here it will come in anti-clockwise in nature and here it will be anti-clockwise in nature. So this will give me the value of ADL1 and that will be for BA, and this will give me the value of ADL1 that will be for BC. Because why? Your ADL1 value, it is equal to, it is at your first coordinate, so it will be summation of friction moments of BA and BC. So ADL1 that will be your MFBA plus MFBC. Okay, and second ADL2 that will be what? It is at your second coordinate is point C. So for this you will be having MFCB over here. So ADL2 that will be nothing but MFCB. So at this point B, I'll get BA and BC, that is ADL1 for BA and ADL1 for BC, and point C I'll get again clockwise restoring moment, that will be your ADL2 and that will be for CB. So I have to calculate these friction moments here. Okay, so first I'll calculate the friction moments. In friction moments we'll be having first MFAB, next MFBA, MFBC and last is MFCB. So one by one we will see this. MFAB provided point load to you. So for that MFAB will come minus WL by 8. Okay, so W, that is 24, L is your 10, so 24 into 10 divided by 8. Okay, along with this what you are having, one condition is provided, that is support B, it is sinking by 30 mm over there. So that will introduce the translation rotations on your BA and BC member over there. Okay, that means if you see this, that is this joint B, it is deflecting by an amount 30 mm over there. Okay, so due to which what will happen, this will introduce the translational moments at your both these joints in anti-clockwise and clockwise nature over there of intensity 6 EI delta upon L square over there, whereas this delta will be equal to your 30 value. Okay, so you have to consider these values also while calculating the friction moments along with the given loadings. So for given loading you are having this minus WL by 8, and along with that this 6 EI delta upon L square will be considered this. So we consider here restoring moment sign, so this will be your anti-clockwise, restoring will be again clockwise, so this will come minus 6 EI delta upon L square, and L is again 10 over here. Okay, negative is why here we consider clockwise, negative sign over here. Okay, so that is you are considering restoring moments, or if you consider directly anti-clockwise as negative, so you will get minus 6 EI delta upon L square. Okay, so you calculate this is WL by 8, W is 24, L is your 10 divided by 8 minus 6 EI, delta is provided to 30. So in meter if you calculate this will get as 0.03, EI is 3800 divided by 10 square, I get this value as minus 36.84 kilonewton meter. Okay, same way MFB I will calculate, that is your plus WL by 8, okay, plus WL by 8, and this same restoring moment will be there, that is minus 6 EI delta upon L square again. So if you calculate this will be, and minus 6 EI delta upon L square, so I get this value as plus 23.16 kilonewton meter. Same way MFBC, that will be again for BC point load minus WL by 8, but this friction moment here will get plus 6 EI delta upon L square. So if you substitute the values, W will be 12, L is again 10 divided by 8 plus 6 EI delta upon L square, L is again 10 square, I get this value as minus 8.16 kilonewton meter. And the last value, this is again plus WL by 8 plus 6 EI delta upon L square, so that will be plus 21.84 kilonewton meter. So these are the friction moments that I am getting over here. Because of sinking support conditions, you need to consider these conventions over there, that is due to the moments occurring due to translation rotations that you have to consider. If sinking support condition is not given to you, then your friction moments will be only due to the applied loads over it. Okay, so considering these values, we will calculate our ADL1 and ADL2. So ADL1, it is your friction moment of BA plus BC. So BA I am getting 23.16 and BC minus 8.16. So this gives me total 23.16 minus 8.16, that is 15. Okay, and ADL2, that is equal to your value of MFCB. So MFCB is your 21.84. So that is your ADL1 and ADL2 values. Next we will go for your stiffness matrix. So S matrix, that is your S11, S12, S21 and S of 22. So in that first Roman we will see, for first Roman what we do, we apply the unit positive displacement at your coordinate 1. So here I will write applying unit displacement at coordinate 1, keeping other coordinates fixed. Okay, that means what you have to do, you have to apply coordinate BA. We are seeing for theta B value. So here your theta B will be equal to 1, that is nothing but your D1 value, right? So I will draw the diagram for that. So your A is already fixed, and we have to fix the remaining coordinate, that is your C. B will remain as it is free. Now I'll mark here my stiffness coefficients. So here I have told you stiffness coefficient you have to mark at first and second coordinate over here, because here we are having only two coordinates, both in clockwise direction, right? So here for first you will be having S of stiffness you are calculating at first coordinate when unit displacement is applied at first coordinate, so you will get S of 1 1. Here S of stiffness you are calculating at your C point, that is at second coordinate when unit displacement is applied at your first coordinate, so that you will get S of 2 1. Now if you see deflected pattern from this side which your moment this S11 originate, that side will be your deflection pattern, so it will come in this way. And for BC it will go in the downward direction, which shows this slope value, that is D1 will be equal to 1, and same way here also D1 will be equal to 1. Okay, we'll calculate your values of S of 1 1. So S11 will be equal to the summation of the two members, that is BA and BC, and that will be your near end acting. Because why? You are applying unit displacement at point B, and B itself you are calculating stiffness coefficient, so that will be your near end. So it will come 4 EI theta B upon L for BA plus 4 EI theta B upon L, and that will be for BC. So theta B here is 1, L for BA is 10 and L for BC is again 10. So this you get 0.4 plus 0.8, that is S11 I get equal to 0.8 times of EI. Okay, so S of 11 I have got equal to 0.8 times of EI. Now next I will calculate S21. So S21 as compared to your applied unit displacement, this will be your far end over there. So S21 will be subjected to far end moment coefficient. So it will be 2 EI theta B upon L. Again B is theta B is your 1, length is 10. So 2 by 10, this I will get as 0.2 times of EI. So S of 11 I got 0.8 EI, and S of 21 I got equal to 0.2 times of EI. Okay. Now we'll move for your second point, that is Roman 2 I will write here. So here what I will do, now I will apply unit displacement at coordinate 2 keeping other coordinates fixed. That means what you have to do, coordinate 2 you are having here theta C value over there. So here what I have to do is the theta C or D2 will be equal to 1 now. That means you have to apply theta C is equal to 1 here. Okay, so I'll draw the diagram again. So here A is already fixed, C we have to keep now released over there, and you have to fix the remaining coordinate, that is coordinate 1, that is your joint. B will be fixed now. So I'll again mark here my stiffness coefficients over there. So stiffness coefficient here I'll get, that is the first coefficient at your first coordinate, second coefficient at your second coordinate. This will be S of stiffness you are calculating at point C, so that will be S of 2, that is second coordinate, when unit displacement is applied at coordinate 2. So this will become S of 2 2. This will become S of stiffness you are calculating at point B, that is your first coordinate, when unit displacement is applied for your second coordinate. So that will become S of 1 2. Okay. Now if you see for this clockwise rotation over there, that is moment will be originating from the topward direction, and which will show again here, that is D2 will be equal to 1. Okay. So I'll calculate the values of this S of 1 2 and S of 2 2. I'll calculate S of 2 2 first. You are applying unit displacement at your second coordinate, corresponding to that C will be your near end rotation. So that you will get as 4 EI theta C upon L, and that will be for your member CB. Here theta C will be 1, length is again 10, so this will get as 0.4 times of EI. Okay. Same way S of 1 2 corresponding to this unit displacement, S of 1 2 is subjected as far end moment, so that will come equal to 2 EI theta C upon L, and that will be for only BC. For BA this moment will not come, because why? AB is completely restrained for slope over there. So that is why here 2ei theta c upon L, that for BA member will be 0. So this if I calculate, again theta c is 1, length is 10, so I'll get this equal to 0.2 times of EI. We'll check whether your S of 12 and S of 21 value is getting same or not. S of 12 I am getting 0.2 EI, S of 21 I have got equal to 0.2 times of EI. Okay, those are same over there. That means your analysis is okay. Now I'll substitute all these values in our basic equation over here. Okay, so basic equation, that is F1 and F2 value, both values I am getting 0 is equal to, next is your AD L1 and L2 values, that is this one 15 and 21.84. Next, plus from all the ES terms I am having EI common, so I'll take that common here. S of 11 I am getting 0.8, S of 21 0.2, 0.8 and 0.2, S of 12 again 0.2 and S of 22 I am getting as 0.4 into D1 and D2 as my basic unknowns here. So if I solve these, I'll get two equations from this. That is your first equation will come 0.8 times of D1 plus 0.2 times of D2 is equal to minus 15 upon EI. And second equation I'll get as 0.2 times of D1 plus 0.4 times of D2 is equal to minus 21.84 divided by EI over there. So that will be your equation number 2 here. Okay, so if you solve these two equations simultaneously for the values of D1 and D2, D1 I'll get equal to, D1 is nothing but your value of theta B and D2 is nothing but your value of theta C that we have assumed in our first step. D1 is theta B and D2 is theta C over there. So if you solve these two equations simultaneously, I am getting D1 is equal to minus 5.828 divided by EI and D2 as minus 51.68 divided by EI over here. So this gives me the value of my basic redundant values or basic unknown values over here. Now what we'll do, we'll try to calculate your support moments here from this. Okay, so for support moment, what you have to do, the next step is you have to plot the slope deflection equations over here. So next is your slope deflection equations. In that, first equation will be for MAB, that is what, equal to MFAB plus 2EI upon L into bracket theta A, but here A is your fixed one, so that will become 0. Just what will remain, theta B and delta will be again 0. So MFAB that we have calculated equal to minus 36.84 plus 2 upon length is 10, so this will become 0.2 EI into theta B. Substitute the value of theta B over here, that is we are getting minus 5.828 over there. So from that I am getting MAB is equal to, here remember sinking support condition is provided to you, but here you have to not substitute the delta value. Why? Because already that delta we have considered while calculating the fixed moments. If you are considering it here, then do not consider it in again slope deflection equations. Getting? So this substituting theta B over here, that is minus 5.828, I get MAB is equal to minus 38.005 kilonewton meter. Same way I'll calculate MBA, that is equal to MFBA is equal to 23.16 plus 2A upon L will remain same again, that is 0.2 EI into bracket 2 times of theta B, because near end will be now B over here. So if we calculate this again substituting value of theta B, I have got MBA is equal to 20.828 kilonewton meter again. Next we'll see for MBC. MBC is equal to MFBC, that is your minus 8.16 plus 2E upon L. L for again BC is 10, so that again same I'll get 0.2 of EI into bracket near end is B, far end is C, so this I'll get as 2 theta B plus theta C. So if I calculate this MBC, substituting theta B and theta C, I have got MBC is equal to minus 20.828 kilonewton meter. And the last value, that is MCB, is equal to MFCB plus 21.84 plus, this will remain again constant, that is 0.2 times of EI theta B plus 2 times of theta C. I am getting MCB here as 0. MCB equal to 0. Now we will check conditions of equilibrium over here. That is at B, MBA plus BC shall come equal to 0, and at C your MCB shall come equal to 0. We will check this. See, MBA plus BC, if you add this, you will get that 0, and MCB also I am getting equal to 0. Now we will try to plot the bending moment diagram from this by superposition. So this is my A, B, C here. Okay. At A, I am getting moment equal to 38.005. Negativities. So using sign convention, this will be plotted on the upward side over here. 38.005. Next, MBA positive, I am getting 20.828. Again, it will be plotted on the upward side over here. 20.828. Same value I am getting for BC, minus 20.828. So it will be plotted on the upward side for BC member. And here at C, I am getting that equal to 0. So I have to join these by straight lines. Next, we will calculate the span moments over here. Span moment for AB and span moment for BC. In both the spans, we are having point load over there. So for that, you will get WL by 4 and WL by 4. So this will be a 24 into 10 divided by 4, and this will be 12 into 10 divided by 4. So this I have got equal to 24 into 10 by 4, this I get as 60 kilonewton meter, and this I'll get as 330 kilonewton meter. Okay, in both you will be having a triangular pattern over there. So for first I am getting equal to 60. 60 is equal to WL by 4, or you can calculate this by WAB upon L also. That will be also, from that also you will get correct value. And BC I am getting equal to 30. So that will be also follow triangular path lower than this 38 value. So somewhere here 30, that is again WL by 4. And just what you have to do is you have to shade this superimposed part over here. Okay, this gives me BMD by superposition. Okay, in this numerical we have conducted the change, that is what sinking support conditions we have seen. If sinking support condition is provided to, then how you have to calculate the moment values over there by considering those sinking support condition in your fixed moment values. If you are considering those in fixed moment values, do not consider them in the while calculation of slope deflection equation. So if you consider here also, those will be getting considered twice, and your values will come wrong over there. Okay, so this will be your second numerical that will conclude over here. If you are having any query in this, you can comment me. Thank you so much.